Welcome. So in this video we will learn how to determine the particle size by laser diffraction technique. Now laser diffraction is based on the principle that when a laser light is allowed to pass through the particles of different sizes, particles will scatter the light, and this phenomenon is known as laser diffraction. So the angle at which they will scatter the light and the intensity of the light will be the characteristic of the particles of definite sizes. This is the basic principle of the laser diffraction technique. That is meant to say that when a laser is passed through the particles, they will scatter the light at different angles, and also at different intensity. And that is meant to say that particle size is the function of angle of scattering as well as the intensity of the scatter light. That is, if we have small particles in the solution, they will scatter light to larger angles, with lower intensity, and if we have large particles in the solution, they will scatter light to small angles with higher intensity. Now this is the basic principle of determining particle size in a solution by laser diffraction in any of the instrument. Again repeating, तो इसका बेसिक प्रिंसिपल यही है कि जब लेज़र लाइट स्ट्राइक होती है पार्टिकल्स को, तो पार्टिकल्स लाइट को स्कैटर करते हैं डिफरेंट एंगल्स पे, और उनकी इंटेंसिटी भी डिपेंड करती है कि पार्टिकल साइज के ऊपर डिपेंड करती है कितनी इंटेंसिटी से लाइट स्कैटर हो रही है. तो कहने का मतलब क्या है कि पार्टिकल साइज फंक्शन है कि इसका एंगल ऑफ स्कैटरिंग था और आल्सो इंटेंसिटी ऑफ द स्कैटर लाइट. एंड वी आल्सो नो दैट द स्मॉल पार्टिकल्स दे स्कैटर द लाइट, जो स्कैटर करते हैं वो लार्जर एंगल पे करते हैं विद लोअर इंटेंसिटी, वेयर जो लार्ज पार्टिकल्स होते हैं वो स्कैटर करते हैं लाइट को स्मॉल एंगल्स पे विद हायर इंटेंसिटी. और ये एंगल ऑफ स्कैटरिंग और जो इंटेंसिटी है लाइट की, जो स्कैटर लाइट की जो डिटेक्टर ने डिटेक्ट की है, वो डिटरमाइन करती है कि पार्टिकल साइज कितना है पार्टिकल्स का सोल्यूशन के अंदर. तो ये बेसिक प्रिंसिपल है, इसके बारे में डिटेल में भी हम कमिंग स्लाइड्स में पढ़ेंगे. लेट्स स्टार्ट. So what do we mean by laser diffraction? The slide shows the basic phenomenon of laser diffraction. In this we can say that light scattering pattern is shown from a group of particles. Now here at the center we have the central spot, and then we have ring formation around it, and then the intensity of these rings as well as the spacing between the rings is the characteristics of the particles present in the solution, and will determine the particle size through applying different models which we will discuss in the coming slide. So this is basic phenomenon, very basic thing, that whenever a laser light is allowed to pass through the group of particles in a solution, they will show some scattering pattern. Mainly this type of scattering pattern is shown. At the center we have central spot, and then we have different rings, and the spacing between the rings as well as the intensity of the rings will be the characteristics of the particles of the specific sizes. This is the basic principle of the laser diffraction technique. Now here we can see that if the particles are large, then they will scatter light to a smaller angle but with greater intensity. And if the particles are small, then they will scatter the light to greater angle but with lower intensity. So same thing which I have told you, and this will decide their particle size by applying different models in the instrument. Now this is master size 3000 optics, that what are the components are there of the instrument. Then one is a laser light will be there, that will pass through the mirror. Here it is one mirror that will focus the light coming from the laser onto the range lens. So this is the range lens, Again, this light will focus the light that is the coming this here it will be sample. So this laser light will be striking the particles in the sample, and the scatter light will be focused by the lens to the beam splitter. Then beam splitter will divide the path of the light to different parts. So it will divide the path of the light into different paths, and then they will be reaching, the light will be reaching to the lens array, and again which will focus the light coming to the detector, and ultimately which will be detected by the detector will detect the light, and then this is passing to the focal plane, and then there is also a transmitter. So this is the basic components in a master sizer 3000 optics, that we have lens that laser light is passing through it from the laser, and then it will focus by the mirror, and then it is passing to the sample where the scattering will happen, and then the light will be reaching to the range lens where the focusing of the light will happen, and the beam split will divide the path of the light into different paths, so that intensity of the light scattered at all the different angles is detected by the detector. And then we have lens array also, which will focus the light to the detectors so as to improve the signal. And then we have the transducer also, which will convert the intensity generated signal to the data in the instrument. Okay, this is the basic simple. So major thing is that we have a laser, and then we must have a sample and also detector to detect the intensity of the scattered radiation, and then these detectors are placed at different angles so that angle of scattering can also be measured. This is the basic principle. Now if you see that this type of the graph this screen will come in the instrument. So when we are measuring the background means if we are circulating only water, and then scattering will be there only by the water particles, and also from the some scattering will also be there from the window of the cell. So this is background signal. So here we can see that 0 to 60 these are the detector numbers. These are the detector numbers, and this intensity is showing at the lower numbers. This means that the large particles are there in the solution. And this is the laser light. Generally we have to take the power of laser light as 70 to 90%. Generally it is taken like this, because if we are taking greater than 90%, then the detector will get saturated, and if it is less than 70%, then we don't have get the sufficient intensity of the scatter light. So that is why that is kept between, generally is kept between 70 to 90 degrees Celsius. Although if there are more concentrated solution are there, we can kept it even less than 50% also, and if more diluted solution are there, then we can increase the intensity to 90%. So that we have to optimize. Otherwise, for most of the sample we are keeping the power of the laser as 70 to 90%, so as not to saturate the detector, and also have to have sufficient intensity of the scatter light in the instrument. So that's the reason. And this background spectra to be removed. So when we add the symbol, so it will automatically remove the background, and then we will have the values for the distribution, intensity distribution of the particles which are present in the solution. Now if we have coarse particles in the solution, so I was already told that if large particles are there, they scatter light to a lower angles with lower angles. That is lower detector reason lower detector will detect the scatter light, and lower angles with greater intensity. So this is intensity distribution. Intensity distribution. This intensity distribution will be compared with the theoretical models which are there in the software. Theoretical models, it will be comparing it with the theoretical models. Theoretical models in the software, and in the converting this intensity distribution curve will be converted to size distribution curve, size distribution pattern. By applying different types of model, that model we will study. One is my theory, other is Fraunhofer theory, that will coming in the coming slides, that we will discuss. Fraunhofer theory. these two types of theory which are involved in determining the particle size of the particles in any solution. Again repeating that if we have a larger particle in the solution, they will scatter the light to a lower angle with greater intensity, as shown in the graph, that the lower detector numbers are detecting the signal, and if we have large particle scattering is considered in the low angle region with corresponding to the low detector numbers, and if we have small particles, small particles scatter light at higher angles and which produce the data in the high detector limit. So we can see that this is bimodal distribution is there, that is when two population sizes are there in the solution. So again this is smaller particles, and this is larger as compared to it is larger particles, because larger particles they scatter light to a lower angle and detected by the lower detector number region, whereas the small particles they scatter light to a greater angle which detected by the larger detector number region. So here we can see again one more thing here to tell you, that the two types of light are used, laser lighters are used. One blue light is also used, that is for detecting the small particles, and here also we are using the red particles, which is detecting the broad range of particles. So instrument uses both blue light and red light for determine the wide range of the particles in the solution. So we see that it is measuring the instrument is capable of measuring the size of 0.1 micron to 1000 micron meter. This much broad range of the particles can be determined, and the size of the particles can be determined by the instrument, that we'll see in the coming slide also. Now coming to the theories which are involved in determining the size, one is the Mie theory. If you see Mie theory, consider the three phenomena of the interaction of the light with the particle. One is the diffraction is happening, then refraction and reflection also. So scattering also it is considered in refraction, also diffraction, and it is valid for the particles having small and transparent particles. So here we see that it is valid for the small and transparent particles. So this is scattering, this is refractive index, and then absorption, small and transparent particles, it is valid. And this model, that is meant to say that Mie theory is considering the refractive index of the particle, refractive index of the medium also, and also the angle of scattering. Of the three components are considered while determining the size. In Fraunhofer theory, the particles are Fraunhofer theory is applicable for the large and opaque particles, and only the diffraction is considered in this. Diffraction and refraction is considered only in this case, where light bends around the edges of the particle producing a scattering pattern. So there is no complex equation, only that whatever d is there, that the size of the particle is inversely proportional to the sine theta. That is, more is the scattering angle, less will be the size, and lesser will be the scattering angle, more will be the size. Simple this relationship. No refractive index is required in this case. Fraunhofer theory में कोई refractive index ना तो particle का ना medium का involve होता है, तो ये simple applicable होता है. लेकिन Fraunhofer theory जो है जनरली उन particles के लिए available होती है जिनका size जो है greater than 10 micron होता है. ठीक है. Now if we compare the Fraunhofer the diffraction theory with the Mie scattering story, then it is applicable for the particles much larger than the wavelength of the light, that is greater than 10 micrometer, whereas it is applicable for the particles of all sizes larger and smaller than the wavelength of the light. So it is more applicable, more scope is there for the Mie scattering. That is why mostly this theory is applied in the instrument. Then light scattering, we say the primary consider diffraction as the interaction mechanism. It considers both all the diffraction, refraction, and reflection as the interaction mechanism. Then large particles scatter light at a smaller angle, small particles scatter light at angle, this we know, and this intensity depends on the particle size, refractive index, and the scattering angle with a complex pattern. So this intensity is depending on the particle size, function of intensity, the function of particle size, refractive index of the medium, refractive index of the particle, and the scattering angle with a complex equation. So here it's simple equation, d is inversely proportional to sine theta, and the intensity distribution curve which will come, that intensity distribution pattern which will come, that will be converted to the size distribution pattern. And different values will be arrived at. Now there is no simple direct relation, relies on the complex equation to relate the intensity and the size. Intensity of the scatter light is a function of diameter, refractive index of the medium, reflection of the particle, and the wavelength of the light. Here we can see that. Then particle size distribution determined by measuring intensity at different angle, primarily focusing on the large particles. This is determined by fitting measured intensity to the theoretical patterns arranged across the wide range. And if you see that this is less accurate for the small particles, less than 10 micrometer, because in reflection, and absorption effect, Mie theory is accurate for some micron nanoparticles also, accounting for wide range of the optical fiber. So these two theories of models are built, and then comparison is done with the theoretical models. which are there in the instrument, and then we will have the size distribution of the particles in the solution, and then different values will be there in the result. So what all values that we can see here. So here we see that if a solution is having a large number of small particles, then Frohn approximation will overestimate the small particles, that is the indicating in the graph. So if a solution is there which having more of the small size particle, then Fraunhofer approximation is overly estimating the small particles. So if Fraunhofer approximation applied for samples containing an appreciable amount of small transparent particles, significantly large amount of sample particles may be calculated. Now, what are the values after the we have analyzed the sample in the instrument? What all values we are getting, that we will see now, and that is the particle size distribution statistics. So one is the median, that is midpoint of the distribution. Mode is the most commonly occurring size class. So here, if the monomodal distribution is there, then median mode is at the same point. Here in the Gaussian distribution we can see. So median is actually the midpoint of the distribution, that is 50% of the particle is less than this size and 50% of the particle are greater than this size, and then mode the most commonly occurring size class in the sample, that is given by the mode. Now if the distribution is bimodal, so the distribution shape is more complex, then this parameter may diverge. Here we can see that the 49% are less than the median size, and then 50%, 1% are more than the median size in the sample, that is seen. And then this is because that decimal point approximation is there, so that is there. Otherwise it is indicating, median is indicating that 50% of the particles are less than this size and 50% of the particles are greater than this size. This is also known as D50 value. Now coming to volume weighted weight, this is the most important parameter which is arrived after analyzing the sample. D43 value, this is the mean diameter, giving more weightage to the volume, and D43 is sensitive to the changes in the coarse particle fraction. Coarse particle fraction means that if we have say two solutions, this is a solution A, this is a solution B, and say D43 value is 2 and B D43 value is 4, that this means that B is having more number of the large particles as compared to the A. B is having the more number of the large particles, so it is sensitive to the change in the coarse particle fraction, and is also monitoring milling. Milling means that if the particles are being broken down in milling, and then if the D43 value is not decreasing, then we will say that milling has not been taken place. Whereas dispersion, it also indicates dispersion, that if proper dispersion is there, if the particles are not aggregating, then D43 value is increase, indicate that particles are not stable in the solution. Okay, so this way it is useful for monitoring milling and the dispersion. Now this is the formula, that is if say d centimeter size particle is there, that is d centimeter, and number of particles is say 3, then 3 into say 1 centimeter is 3 into 1 power 4, that is the meaning. So say in the solution we are having 1 centimeter size of say 3 particles are there, 2 centimeter size of the say 2 particles are there, and then 3 centimeter size of say 1 particle size is there. Then how to arrive at D43 value, that calculation we see in the coming slide. Otherwise, what do you mean to say that if D43 value is higher, then large particles are present here. So if you compare these two and this, that is it is having 11.2. so blue sample is having large particles, whereas green line sample is having the lower size particles, small size particles in the solution. So the instrument is giving all these values. The D10 value will give, what do you mean by D10 value? That 10% of the sample are less than this size. 10% of the particles are having a size less than 2.55 micron. D10 value 50 means 50% of the particles are having less than 4.92 value, and D90 means 90% of the particles are having size less than 30.6 values, and D32 means that it is the surface area weighted within, that we'll see in the coming slide. And if we compare these two samples, this means that small size particles are more in the case of 8 number sample, and if we compare these two, that then we say that large particles are more in the case of size 7 sample. Okay, so these are the significance of these values, and these values are arrived on analyzing the sample in the instrument. Okay, and these values have significance, and which values to be used for what kind of application, that can be arrived at, and where considering that the changes which we are expecting and the type of particles which can be there in the solution, this parameter to be selected. Otherwise the instrument is giving all these values for the particular kind of sample, and we can interpret the results accordingly. Then come the surface area weighted mean. Here it is sensitive to the change in the fine particle fraction. That means to say that if we have a sample A and B, and D3 value of sample A, say this is A, and this is B, and D3 value of sample A is 2 and say B is 4, then sample B is having more number of the small size particle. That is the meaning. And this is the formula. Now we'll see the calculation also in the coming slide. Then D10, D50, D90, D32, D43, all these values will come in the as a result in the instrument. Now just to show you how the D43 is calculation, say in a sample we have 1 centimeter size particles, 2 particles are there, 2 centimeter size particle, 3 particles are there, 3 centimeter size particles we have 1 particle. Then how to arrive at D43 value? We see that formula is Ni4 divided by Ni3 sigma. So this way we are calculating D43. Now for calculating this numerator, that here we can see that n1, that is n1 is 2, so 2 into 1 power 4, that is 2, and here it is 3 into 2 power 4 is 48, and here 1 is 1 into 3 power 4, that is equal to 81, and then if you add it, then it is 131. Now step 2, you calculate the denominator is again 2 into 1 cube, that is 2, 3 into 2 cube 24, 1 into 3 ka cube 27, you added 53, and this should divide 131 by 53, you will have 2.48. That is the meaning that D43 has arrived this way. This is the formula of D43, that is number of particles of a specific size or specific diameter is calculated, is multiplied, and then we do the summation of all the particles of the sizes, and depending on the number of the particles we will have the numerator value first and the denominator, and we divide it, then we will have the D43 value. This way we are calculating the D43. Now if you see D3 calculation, so this is not D43, this is D3 calculation. So this is the 3 calculation. If you see here is 2 into 1 cube, that is we are calculating the numerator here, that is Ni3, that 2 particles of 1 centimeter size, 3 particles of 2 centimeter size, 1 particle of 3 centimeter size. We will have the numerator as 53. Now here also if we calculate the denominator, then we have 2 particles of 1 centimeter size, 3 particles of 2 centimeter size, 1 particle of 3 centimeter size. Then if we sum it 23, and then if we divide the 53 by 23, we will have 2.3 as the D32 value. Okay, so this way we are calculating the D43 and D32 values. If somebody asks you the numerical also, then you can solve it. Now coming to another parameter which is known as span. This is the span which is indicating the distribution of the particles or the variation in the size of the particles. So span means if more span value is there, then more variation in the particles. So here we can say that for blue size sample we have broad value of the span, whereas for the green color sample we have the lesser value of the span. This is narrow sample span is 0.695, it is 8.619, and the formula is D90 minus D10 divided by D50. This is the formula of the span, simple a formula. And then here we can see the variation in the size of the particle. More span is there, then the variation is more, that is broad range of the particles are present in the sample. If the span is less, then the narrow range of the particles are present in the sample. That is the meaning. Now how to choose? So choose a parameter which that is sensitive to the changes you wish to monitor. So whatever I told you, as I already told you, that what type of application you are having, depending on that you can choose the parameter. If you are thinking that there will be changes in the small size particle, then you go for D32, and you are expecting that there will be changes in the large size particle, you go for D343, and then as already told, that instrument is giving all the values, and like D10 it will give D50, D90, D32, D43. So all values are giving, and the interpretation can be done after running the values. Now if we compare two instruments, one is Malvern master sizer and a Malvern zeta sizer, both the equipments we are determining the particle size. The Malvern master sizer is based on the principle of laser diffraction, whereas a Malvern zeta sizer is based on the principle of dynamic light scattering as well as electrophoretic light scattering. That is the meaning. This is the laser Doppler electrophoresis laser Doppler electrophoresis. Now size range, I already told you that it is measuring the size of the particles in a solution ranging from 0.1 micron to greater than 1000 micrometer, whereas Malman Zeta sizer is measuring only for the particles in a solution ranging from 0.3 nanometer to 10 micrometer only. The principle is different, then particle size difference. What all results we are arriving, we have D10 value, D50 value, D90 value, D43 value, D32 value will come in the instrument, whereas in the master sizer only we have 3 values. One is hydrodynamic diameter, that is Z average will come, zeta potential will come, that is in millivolt, and polydispersed index, that is the indicating the uniformity of the particle. So PDI is higher than more broad size of the particles present in the solution. Now sample, which type of sample types can be analyzed? In the case Malman statin, we are analyzing the dry powder also, we are analyzing the liquid suspension also, whereas in the case of Malman Zeta sizer only liquid suspension can be analyzed, powder particles cannot be analyzed. Now it is best for the broad particle size distribution. Large particles are there, it is best for the narrow size particles, that is generally it is mentioning the nanoparticles, colloids and proteins. So these are the differences between the Malman master sizer and Zeta sizer. So depending on your sample, depending on the size of the particles expected in the sample, we are deciding the technique which one to go for.